welcome to another presentation. We're talking today about surds, but before that I just need to set the scene by going back a little bit and giving you a bit of background information. So come with me, if you will, on a little journey. Let's just start with when you first met numbers. Going right back to when you learned to count and when you learned to add things together, all you really needed was what we're going to call the natural numbers. And that's numbers, whole numbers really, starting with 1. So 1, 2, 3, 4, 5, etc. You never really needed anything more than those sort of numbers when you first started to add. Expanding slightly, you then learned to do subtraction, and you would have found at some point that some subtractions gave you answers that weren't in the natural numbers, namely negative numbers or even 0. So we need to expand this set into the set of integers, which includes things like 0, minus 1, minus 2. Notice natural numbers is a subset of integers, but integers has got other things in it that are not natural numbers. So that's all well and good, and then you learn to do division, and occasionally you'll be dividing and you'll get fractional answers. So we need to expand our set of numbers that we're working with even further, from integers to rational numbers. And again, just examples of half, a quarter, 5/7. There's all sorts. And remember, each one of these sets contains the previous one within it. So integers can also be rational numbers because they can be expressed as a fraction. That's what rational numbers really are. Moving on then from rational numbers, where we've done division, multiplication, addition, subtraction, all of those operations can be performed within these sets, particularly the rational numbers. But then we expand to different sorts of calculations where you might have to square root or use trigonometric functions. Then we need to expand the set even more to the set of real numbers. The real numbers are all of these previous ones, rationals. They can be expressed as fractions, as whole numbers. Remember, decimals can be recurring or they can be terminating, both of which come under the classification of rational numbers. But then we've got things that can't be expressed as fractions, and those are things like irrational numbers. And an example would be pi, or another number called e. But more specifically, and that's going to be the focus of this presentation, is surds. And surds are numbers with the square root left around them. But more specifically, they're left with the square root around them, and the number inside is not a square number, for example root 2. All of these numbers cannot be expressed as fractions, therefore they're not rational. So because these are called rational, these have to be irrational. It doesn't mean that they run around with strange fears and phobias and panic, it just means they're not rational. So the set of real numbers is made up of things that can be expressed as fractions, things that can't be expressed as fractions. That's really all we need to go to at the moment, but just for the sake of completeness, if you're trying to, for example, square root a number, and the number you're square rooting is negative, then that has no solution within the real numbers. So we have to extend our number sets that we're working with to introduce what are referred to as imaginary numbers. Now this is going beyond what we need at the moment, but say for example the square root of minus 36. Now again, just because some of you will want to know, the answer to that is 6i. Or 6j if you're an engineer. But real numbers and imaginary numbers together make up the set of complex numbers. And the thing with imaginary numbers, it's not that they don't exist, it's just once somebody named these the real numbers, where do you go from that if they are not real numbers? Well, some bright spark came up with the idea of imaginary numbers, but they certainly exist and they're used a lot in engineering. But I digress. Here you can see the notation that's used for each of these sets, and sometimes they're modified slightly to just talk about the positive numbers or the negative numbers. That notation, it will come up in certain questions, but that tends to be reserved mainly for A-level type problems. So let's move to the focus of this, which is surds. Now the things that you're going to need that are going to be useful for this presentation are an understanding of square numbers, understanding of factors, FOIL meaning the way a mnemonic for expanding two pairs of brackets, and for some of the latter examples which are possibly beyond GCSE, the ability to recognise expressions that are the difference of two squares. The thrust of this presentation are these two facts here. If you've got a number in the square root, namely a surd, and that surd, the number inside the square root, can be expressed as a pair of factors, then the square root of AB is the same as the separate square roots of A and B multiplied. In other words, the root of a product is the same as the product of the separate roots. How is that used to simplify? Well, if we can find a factor of the original number, in this case either A or B, that is itself a square number, then rooting it will actually simplify it and give you a part of that expression that's rational. And a smaller surd is considered simpler. So let's look at root 18 and then we'll come back to this other property here involving a ratio, a quotient. So the root of 18. Now what I want is a factor pair of 18. So I could write root of 2 times 9. Similarly, that's the same as the root of 3 times 6. Now only one of those contains a square number, so that's the one we really need to focus on, because the root of 3 times 6 can't really be simplified. Root 3 times root 6 doesn't make it any simpler. So we'll neglect that one and we'll focus on this one. So using that fact above, that's the same as the root of 2 multiplied by the root of 9. And we know that the square root of 9 is 3, so that simplifies down to 3 root 2. We could put plus or minus in front, because you remember whenever you square root you potentially get two answers, but that tends to get relaxed in these sort of questions because you're generally just simplifying. Let's have a look at root of 80. Well, what two numbers multiply to make 80, one of which is a square number? And we're looking for the biggest square factor, so we could have square root of 16 multiplied by 5, because that's the same as the root of 16 multiplied by the root of 5, which in turn simplifies down to 4 lots of root 5. Right, the next one. If you're asked to simplify the sum of two surds, we're really looking for them to be multiples of the same surd. So root of 50 we could write as the root of 25 multiplied by 2, and the root of 72 is the root of 36 multiplied by 2, which becomes root 25 multiplied by root 2 plus root 36 multiplied by root 2. Simplifying both of those, that's 5 root 2 added to 6 root 2. Now because they're multiples of the same surd, that is 11 root 2. And that would be a simplified end result. This fourth one picks up the other property at the top here. The root of a fraction is the same as the root of the numerator divided by the root of the denominator. So let's have a look at this. This is the same as the root of 32 over the root of 49. Well, the bottom will simplify straight away, because that is a square number. The top isn't, but the implication is that it will simplify. So root 32 is root 16 root 2 which in turn is 4 root 2 over 7, or 4/7 of root 2. Number 5, this is where we need the FOIL mnemonic, because we're multiplying out a pair of brackets. So the F stands for multiplying the first term in each bracket, so we get 2 lots of root 3. O is the outside term of each bracket, root 3 multiplied by root 3. Well, root 3 multiplied by root 3 is 3. The inner terms, 1 multiplied by 2 is 2. And the last term is the 1 multiplied by the root 3, so plus root 3. Those are your 4 terms. We have a rational part, 5 plus, and then the surd part, 2 root 3 plus another root 3 is 3 root 3. So that's simplifying one surd, or a sum of 2 surds, or a pair of brackets. The next type of problem you might meet involves the understanding of equivalent fractions. If we have the fraction 3 over root 12, and the question asks us to rationalize the denominator, then because we now know what a rational number is, it means what we need to do is find an equivalent fraction to 3 over root 12 that doesn't have a surd on the bottom. So we need to find a factor that scales that up, so it still represents 3 over root 12, but it doesn't have a surd on the bottom. Well, the way of doing this is that you simply multiply the top and the bottom by what's on the bottom. Remember, it has to be both the top and the bottom that gets multiplied, otherwise it doesn't represent the same fraction anymore. So what we have is 3 over root 12 multiplied by root 12 over root 12. So that gives us 3 root 12 on the top. What it gives us on the bottom is 12. And these invariably need simplifying further. Well, 3 over 12 is the same as a quarter. So we get root 12 over 4. But in turn, root 12 simplifies further. Root 12 is root 4 root 3 over 4, which is 2 root 3 over 4, which is root 3 over 2. There's lots of places where you could stop with that, but you need to take it as far as it will possibly go so that you're left with the simplest form. The next one, 21 plus 2 root 7 over root 7. Well, same principle again. We multiply the top and the bottom of this expression by root 7. So that gives us 21 root 7 plus 2 root 7 multiplied by root 7, which is 2 times 7, 14. And on the bottom, root 7 times root 7 is 7. This will simplify because the 2 terms on the top are factors of 7, so let's factorize it first. Always good practice to factorize rather than just cancelling out. 7 lots of 3 root 7 plus 2 over 7 leads us to an answer of 3 root 7 plus 2. The last one probably goes beyond the bounds of GCSE into an AS type problem. What we have here is a combination of a rational part and a surd part on the bottom. Now, as you can hopefully appreciate, multiplying this top and bottom by root 3 won't rationalize the denominator because you'll have a 5 root 3 part and a 3. So this bit becomes rational, but it introduces a surd part to here. So this is where the understanding of the difference of 2 squares arises, and that is that if I multiplied that by its conjugate, in other words 5 take away root 3, then when I expanded that out using f foil, the 5 root 3 term and the minus 5 root 3 term will cancel out, which will have the effect of rationalising the bottom. So if I write that down, you'll see what I mean. I'll put the brackets in, although they're not strictly necessary. I'll have 5 times 5, which is 25. I'll put that down now. Root 3 lots of 5 and minus root 3 lots of 5 cancel out, and then I have a plus root 3 multiplied by minus root 3, which is negative 3. On the top, well, let's simplify the root 242. That's root 1 to 1 multiplied by root 2. I'll leave that multiplier in brackets for the moment, because I can simplify the other parts. 11 root 2 lots of 5 minus root 3. On the bottom, 25 take away 3 is 22. So what I will get is root 2 lots of 5 minus root 3 over 2. And that's got a rational denominator, and there is no real point in expanding that further. So with the exception of that last question, question 8, all of those other sort of questions are potentially what could crop up at GCSE AA style level. I hope you find that useful. Come back soon. Bye now.